So shall I start?
Yes, sure. Yeah.
Okay. So welcome everybody to the second lecture on the combinatorics of the symmetric functions related to Macdonald polynomials. So let me share the screen. Okay. So last time we defined the Hall-Littlewood polynomials. This time I can see. So I defined them following Macdonald in a kind of brute force way as this sum. These involve parameter t, and we'll call the set of symmetric functions whose coefficients are polynomials with integer coefficients in t as lambda adjoint t. And if we fix the number of variables to be n, then we'll say lambda sub n adjoint. And we define these polynomials are lambdas, and then we showed that they're divisible by these products of factorials, t factorials, t analogs of factorials. And we divided by them to form the fundamental objects known as the Hall-Littlewood symmetric functions P lambda. And we showed that if we set t equals 1, we get the monomial symmetric functions, and if we set t equals 0, we get the Schur functions. So they interpolate between the two. And we showed that they have a stability property, and then we defined another family of symmetric functions by multiplying these p lambdas by, again, some nice functions which are products of t factorial times the power of 1 minus t, and these also turn out to be stable. And finally, we for these q lambdas, if we look at the single row partitions, we found these small q sub r. We found symmetric functions q sub r, small q sub r, and then we defined small q sub alpha to be products of these guys. These will come up in a second. And we defined we gave two formulas for q lambdas, one as a generating function and one in terms of raising and lowering operators. Okay, so that's a quick summary of what happened in the last lecture, sorry. I'm still in teaching mode. So now I want to mention some more properties of Hall-Littlewood polynomials. So the first one I will state without much fanfare is this Peary rule. So a Peary rule is for Schur functions gives you a formula for the product of a Schur function with a complete homogeneous symmetric function, or which is the same as a Schur function with a single row. So analogously, there is a formula for Hall-Littlewood symmetric functions. So let me just set some notations. So the structure constants. Hall-Littlewood polynomials are given by, so if you multiply two of them, so p mu xt times p nu xt, you get a sum over lambda of f lambda mu nu of t p lambda xt. So these are the structure constants. And so these belong to ZT. And the dual Peary rule, so it's easier to state the dual Peary rule, which is, I'll show you in a second. States. So if I take f mu times the partition 1 to the m lambda, this has this product, this nice product formula, so product of I greater than equal to 1 of the t binomial coefficient lambda prime I minus lambda prime x lambda prime I plus 1, choose lambda prime I minus mu prime. So this is the t analog of the binomial coefficient. So please ask if anything is not clear. So this is just the binomial coefficient where you replace the factorials, right? The t analogs of the factorials, which I just mentioned. And this, notice that the lower term has to be non-zero for this. I mean, has to be non-negative for this to be non-zero, and that means that mu should be contained inside lambda. So if this is lambda, then mu should be sitting inside. Okay, for this to be non-zero.
But it doesn't have to be a vertical strip, is it? Or it has to be, right?
Yeah.
I don't quite. How do we see it from here?
No, I don't think it has to be a vertical strip. I mean, it has to be a vertical strip only in the limit t going to 0. We can check this on Sage.
I see.
Yeah. Okay, so so now I want to define the fundamental property of Littlewood polynomials. These are the orthogonality relations. So
I have a question.
yes.
So how come the first rule, that is Peary rule, not involving any complex symmetric function for its generalization?
How come that?
You look at the structure constant, right, for the
Yes.
Peary rule.
Yes.
But for the Peary rule, you want one of them to be the complex symmetric function in classical suit functions.
You want the column sum to be?
I'm saying in classical case, the Peary
Yes.
rule, so
Yes.
suit function is multiplied by the complex symmetric function.
No, this is the dual Peary rule. So you're multiplying it by the elementary symmetric function.
No, I'm saying the previous one as well.
Yes.
The previous one, yeah. Here, where is the complex symmetric function generalization?
No. This is this is the general statement. I'm not stating the Peary rule. The Peary rule would be, the Peary rule would be a statement of the form f lambda mu, the singleton partition m. There's a formula for that also, but it involves a little more notation. So I'm not giving it.
Okay, yeah. Okay, I'm just confused.
This thing is the Peary
Yeah.
rule. A formula for this would be the Peary rule.
Okay.
This is the dual Peary rule because we are multiplying by, I mean, we are multiplying p mu by where the nu corresponds to the single column instead of the single. Okay.
Okay, thank you.
Okay, so so let me remind you of something from Amri's lecture. So Amri had given the following theorem, proved the following theorem, that if you have two bases of symmetric functions, u lambda and v lambda, and they are orthogonal with respect to the the Hall inner product, then if and only if, when you take the sum over all lambda of u lambda in terms of one family of variables x times v lambda in terms of another family y, then you get this product pi of xy, which is somewhere over here. So it's a product of 1 minus x, 1 by 1 minus xi yj. So this generalizes beautifully to the whole little word case. So define an inner product on lambda joint T as a there we go. So using, yes, is there a question? Using the power sums symmetric functions, just who is the power sums by. So I take P lambda P mu. You define them again to be orthogonal, but you define the so let me say sub T. You define the inner product to be so this will take care of the orthogonality. The norm will be given by Z lambda. Sorry. Which was the size of the centralizer, divided by, now there is a factor extra, which is product I greater than or equal to 1 minus T to the lambda I. Okay. So in the limit that when T, you set T to 0, you get the usual.
So Arvind, and you want lambda of T, not lambda Q of T. And you will use lambda Q later on as well.
Lambda Q of T?
Meaning the ground range should be Z here, not Q.
Yes, yes.
Okay.
Yes, yes. Maybe it's convenient for some technical reasons to include ground rent.
I mean, if you are going to use it in Q, you may as well define it over Q right now. But if you don't think you have, then
yeah, I haven't defined it, but at least the P lambdas will be all over the thing. So, yeah, yeah. So this thing is called is denoted Z lambda of P for T. Okay. So the theorem which generalizes that generalizes the theorem that I just mentioned in Amri's lectures is the following.
sorry, on the left hand side, should that be a mu then? Or, yeah.
Yes. Okay, so the theorem that generalizes Amri's the theorem in Amri's lecture is the following. So suppose, okay, so maybe I'll just satisfy Purva. Okay, so suppose U lambda and V lambda are Q bases of lambda Q joint T, then U lambda V mu is delta lambda mu if and only if sum over all partitions lambda of U lambda x T V lambda y T is this thing that we have called capital pi T, where capital pi T is the product over I j greater than or equal to 1 minus T xi yj divided by 1 minus x. So when you set t equals 0, then the numerator becomes 1 and you get this. Okay. So what this says is, so this I will not prove, but this automatically gives you the same kind of, oh, what have I done?
When you put t equals 1, it completely degenerates, is it?
Yeah, so
Or do you
t,
have to take limit somehow? Okay.
yeah, this is not a good limit, I think. Yeah, so then you will get monomial symmetric functions, and
But the left hand side is, yeah.
I suppose you've seen, yeah, no, this doesn't make sense when t is 1.
Wait, it's a product of ones, but that's not good.
Yeah, that's not good, yeah,
But
because,
the left hand side is not constant, right?
yeah, that's the problem.
Ah, okay. Thanks.
So what happens is some way of
Yeah, it's a kind of degenerate limit, it is. Okay, so as corollaries of this, you get the following. So you get three, well, you get three results. The first one is, of course, for p lambdas itself. So sigma sum over, sorry, minus again. Sum over lambda, p lambda x, p lambda y divided by z lambda. Sorry about that. Sorry. This is equal to pi t. So that's just a consequence of the definition. But you get two more results, which are not here. So the first non-trivial result is that the p lambdas which we defined
Sorry, the numerators don't have any t's.
don't have any t, exactly. So the t comes everywhere through z.
Ah.
So because these are the usual power sums, they have no t.
Right.
P lambda xt times q lambda xt, this is. Okay, so unlike the sure case, unlike the case when t equals 0, you don't have you don't have an orthonormal basis, rather. So the p lambdas are dual to the q lambdas. Remember that the q lambdas are just some factor times p lambdas, which that factor becomes 1 as when t goes to 0. Okay, and the third one, I don't know if I define the S lambdas. Okay, so let me define another another basis of symmetric functions. So define, or maybe for lack of time, already done this. Okay, so there's another family of symmetric functions which one can define this way. Oh yes, just a second. Yeah, so remember I defined the q lambdas, small q lambdas. I defined the small q lambdas as products of q sub r, small q sub r's, where r ranges over. It will be small q sub lambda 1 times small q sub lambda 2. That's how I defined it. So if you take small q lambda of x t times m lambda, oh sorry, this should be a y. m lambda of y. This is again y. So this it says that the small q lambda, which we defined in a completely sort of ad hoc way, turns out to be natural to the turns out to be dual to the monomial symmetric functions. So let me show you this on Sage. So this is the same worksheet that I had from earlier. So I define sim, I define all the usual bases, I define P and Q, and so now I define this small q. So this is not inbuilt in Sage, I just made it up. So these are just products of big q's over the ranging over the partition. So for example, small q of 2 1, when you express in terms of big q, it's some complicated thing. And I can define, so Sage has a way of defining dual bases in terms of any inner product that you like. So here I'm defining the Hall inner product. So you take an X and you take its centralizer size in this general sense. So you leave T to be arbitrary. And so to define the dual basis, you have to set T to be the generator of this fraction field. And then I define MD to be the dual basis of the monomial symmetric functions using this inner product. Okay. And if you see, so I can show you what this looks like. So if I say MD of 2 1, it'll use this notation. This is dual of n. That's what this notation means. And if I express the these duals of m in terms of the q basis, I get exactly the same thing over here. And so I can check that, but I can do something more general. So I take MD of law.
Can you explain your definition, how you did the inner product here?
So Sage has this way of so this lambda is just is a it's not shorthand for a function. So it'll take any partition x and it will return this polynomial, which is exactly what I called z lambda of t. Okay, and so if I so if I get the line partitions of 3, say, oops, something went wrong. Okay, let me fix this. No, but it just worked for 2 1. Okay, let me fix this later. Okay, I mean, it just worked for the partition 2 1, which was here. So something. Okay, I'll fix that later. I wanted to define the dual basis in terms of the shores here, but okay. So that is one important aspect of the Hall-Littlewood symmetric functions. And in fact, what one can show, although this is not the tack I have taken, is that the Hall-Littlewood symmetric functions, P lambdas, can be defined in terms of two properties, which is the orthogonality with respect to this inner product, and the fact that its monomial expansion involves only partitions smaller than it, and the the coefficient of m lambda and p lambda should be 1. So this completely defines all Littlewood symmetry. So we'll do something more general, and that's why I'm not going into that detail here. So the next thing I want to do is to show you how to expand the Hall-Littlewood symmetric functions in terms of monomial symmetric functions. So there's a beautiful combinatorial formula. So I want to explain that. So recall that in Amri's lectures he had defined semi-standard Young tableau. So let T be a semi-standard Young tableau, which I'll denote SSYT of shape lambda. Which means that it's a filling of the Young diagram of lambda with positive integers, which are weakly increasing in rows and strictly increasing down columns. So I'll give examples. And I'll denote lambda super I of t to be the subpartition of lambda formed by entries less than or equal to I. Okay, so you look at the tableau filling and you see what all the entries which are less than or equal to this fixed I, and you look at they're guaranteed to form another partition. So we'll call that partition lambda. So because of the semi-standard property, the cells of lambda I of t minus lambda I minus 1 of t are in different columns. So there'll be no two cells in the same column, right? Because it's strictly increased down column. Okay, so here's okay. So I need one more bit of or two more bits of notation. So let j sub k of t be the column indices j such that there does not exist a cell of lambda k of t minus lambda k minus 1 of t in column j, but there does exist a cell of this in column j plus 1. Okay, finally, psi t of small t is the product over all I, product over L in ji of t. Maybe I should use k, just avoid confusion, of 1 minus t to the and the multiplicity of L in lambda k minus 1. Okay, so this is a handful. So the theorem states that P lambda is the sum over all tableau with shape lambda, semi-standard tableau, of psi t of t x to the t, where x to the t stands for x1 to the number of ones in t, x2 to the number of twos in t, etc. So let me show you. I mean, it's really, it's amazing that you get a symmetric function in the first place. Because this formula is so messy. So I can give you the first non-trivial example, the Gelfand principle. So take lambda to be the partition 2, 1, and I'll take the maximum entry.
I had a question, sorry.
Sure, sure.
If you put t equals 0 on both sides, do you recover the little bit definition and whatever? Actually, what do you? Yeah.
You get sure functions, yeah.
Yeah.
You just get the sure function, but it's not immediately obvious.
It is not a sum of weights over semi-standard and
No, it is, right? Because each one gives you one.
Exactly. That gives you 1 and you get x to the t. Right? Okay.
Yes, exactly. So you get sure functions. Yeah, good point. Yeah. Okay, so let's do this. Okay, this is going to be some bit of jugglery. Okay, so I take the partition 1, 1, 2. So maximum entry is 2, so there are only two tableaux. So the first one is this. Okay. So now let us look at these lambda sub i's. Okay. So this implies lambda 0 is the empty partition. That's always true. Lambda 1 is the singleton partition because ones are here. Lambda 2 is the partition 2, 1, which is the original case. All right. So so let's look from here. So let's look at J sub 1. Okay, so we are looking at column indices where there is no cell in a certain column and then there is a cell in the next. But that does not happen for this case because if you in column 1 there is a cell, in column 2 there is a cell, and in column 3 there is no cell. So the only cell, I mean the only column index for which it would happen that there is no cell and then there is a cell is 0, but that's not allowed. So this product is the empty product. Okay, for k equals 1. So so this gives 1 over here. And from these,
Sir,
yeah.
Sir, what is the ML in the formula of psi t?
Okay, let me remind you. So this is the multiplicity. Multiplicity of L in lambda k minus 1.
Thank you.
Okay, so here again there is only one extra cell, and there is no such column index k. So again here you get a 1. So at the end of the day you get psi t of t is just one big fat 1. Okay, so this is the first case. Now let's do the next case. Okay, which I should have said that this is case 1 where I'm taking the coefficient of m to 1 itself, because the content of this tableau is 2, 1. There is 2 1s and 1 2. Okay, the other tableau which gives you the same content is 1 2 1, and so here lambda 0 is empty as before.
Sorry, I'm confused. That's not column strict.
Sorry, 1 2 2. Yes, lambda 1 is 1 and lambda 2 is 2 1. Right, so here there's only one cell, and here suddenly you're going to 2 cells. And now let's see what the size are. So here there is there's no column index for which this happens again. So, this contribution is 1. Here, the new columns are 2 of them. So we have just switched the rows of these guys. So again, it's 1. And so psi t of t. This is as it should be, because you should get the same contribution for both. I mean, it should be a symmetric function, so these two should have the same. Okay, so let us take lambda, or rather mu, to be 1, 1, 1. So content is now 1, 1, 1, which means all three entries are different. And here now t is, let's say, 1, 2, 3. We take that to be the first one. Now something interesting is going to happen. So lambda naught is phi, lambda 1. Now there are 3, it goes up to lambda 3. Lambda 2 is, I have to take the entries less than or equal to 2, so I get the partition 2. And lambda 3 is 2, 1. Okay, so here too, I get a contribution 1. Here is where the first interesting thing happens. Because the new cell is over here. That means, if you go back here, I have, when I take k equal to 1, when I take k equal to 1, there is no cell in column 1, but there is a cell in column 2. And for every such index j, I have to take the multiplicity of 1 in lambda super 1. Because I have to take in lambda k minus 1. Okay, so here I get a factor of 1 minus t to the m1 of lambda 1, which is 1 minus t. Okay, because in lambda 1, which is this, multiplicity of 1 is precisely.
Sorry, I'm confused 1 second. What is the new here? Mu equals 1, 1, 1.
Content. So there is 1, 1, 1, 2.
Okay. Mu is the content. Okay,
Yes, because x to the t is what we are taking. So this will have x1, x2, x3.
That's right. Okay, thanks.
Okay. Right. And here too, if you compare now with these two, the new cell is in the first column, so there's no way you have anything new. No, not the Greek letter. So psi t of t is 1 minus t. And I leave it for you to do the computation. I'll just start it out. I'll write it maybe a little faster. So lambda naught is phi, lambda 1 is 1. Now lambda 2 is 1, 1, because 2 is added over here. And lambda 3 is 2, 1, as always. And here you will get a contribution of 1. Here also you will get a contribution of 1. And here you will get a contribution of 1 minus t squared. Okay. And so the theorem says we have to sum over all tableau. And so this guy will give us psi t of t is 1 minus t squared. And so at the end of the day, what you get at the end, we get that we get that p21 of x1, x2, x3 t is m21 of x1, x2, x3 plus, because the coefficient was 1 and there was only one such tableau, plus 1 minus t plus 1 minus t squared, times M111 of x1. Okay, and this thing, if you factor it, is 1 minus t times 2 plus t. And let me show you on Sage. So if I do m of S2, sorry, m of HLP of 2, 1, I'll get 2 minus t squared times m11 plus m2. Okay. So it's a bit, it's quite intricate, I mean, admittedly, but it's quite non-trivial that it gives you the same, I mean, it's symmetric in variables. So here I should clarify, here I'm taking the max entry to be 3. I mean, I can't take max entry. So, you know, you could have done 1, 3, 4 and, you know, whatever else you want. You will always get 2 tableau, one with 1 minus t and one with 1 minus t squared. And if you take the content to be the same as the partition, you will get exactly 1 tableau in which there's the first, all the rows are constant and increasing term columns. So then you will get exactly 1. Okay.
So if you have 3 variables, x1, x2, x3,
Yeah.
then in all cases you should consider max entry equal 3.
Yes, exactly. But I'm saying that here, if you had taken with content 2, 1, if you had taken 1, 3 or 2, 3, in each case you will get exactly 1 tableau with that content, and that will have coefficient 1.
Okay.
Okay. Here we are doing the opposite. So here we are taking 1, 1 and 2, 2s. So I mean, I guess I mean the content in decreasing order. Okay, so you have maximum number of 1s, next number of 2s. If you go that way, then you will have exactly 1 tableau. Even in the other case, you will have exactly 1 tableau, but it will not have that simple structure. But one can describe it, of course. Okay.
So you're writing the P in terms of the M's, and of course
Yeah.
the coefficients are integer polynomials of T.
Yeah. Right.
Yeah, so how does this relate to the theorem above? Sorry.
So this is what the theorem is saying. So if you
Oh, the X to the T's are the monomial things. You are regrouping them into okay.
So so the claim is that this is a symmetric function, which is already non-trivial.
Right.
Okay. So the last thing I want to say about the Hollywood polynomials is the Koska conjecture. So remember that we expressed in Sage, I showed you how to express one family of polynomials in terms of another. Even Amri showed you that. And we expressed the Hall-Littlewood in terms of the Shurs and the monomials. It turns out that if you express, so this is a conjecture, this was theorem. This was conjectured by Fuchs in 74 and proved by Lascaux and Roger in 78. Is that the Schur function, so when expanded in the p lambdas, s lambda has an expansion has
Is that a lowercase p?
no capital P, the Hollet woods.
Okay.
S lambda has the coefficients of S lambda are integral polynomials in T with non-negative integer coefficients. So let me show you. So here is the expansion of Shores in terms of the Hall Littlewoods, and you will see that these have non-negative integer coefficients. You can go there. Okay. So remember when we went the other way, you have all kinds of signs. So this was Q in terms of M, P in terms of S. You have signs, and you can't predict so easily. But when you go the other way, you always have non-negative integer coefficients. And this was proved by explicit combinatorial formula. So Lasko, Schulz, and Berger defined a statistic called a charge of a tableau, and they expanded. They showed that this expansion can be written combinatorially in terms of the charge. Okay, so so this is what I wanted to say about the Hall Littlewood polynomials. Are there any questions? Okay, so in the last maybe 15 minutes or so, I want to introduce Jack polynomials. I'll say much less than what I've said about the Hall Littlewoods. But I want to mention one beautiful result, which is related. It starts with the Selberg integral. So I think I'll not have time to get into it, or maybe I should just define the Jack polynomials first. Okay, maybe I'll just define the Jack polynomials first, and I'll tell the Selberg integral story. Okay, so let alpha. So this is a completely new family of polynomials. Again, generalizing issues. So let alpha be a positive real number. So we define a new class of symmetric functions. In lambda, so we take the fraction field in alpha by the inner product P lambda P mu, let's say alpha. This is delta lambda mu. So again, we set the power sums to be orthogonal, except that we take the norm to be alpha to the L again. Alpha to the L lambda times it. So this is the same factor we had before. And now we take alpha to the length of lambda. Length of lambda is the number of non-zero parts. And just as we did in the Hall Littlewood case, we define a double infinite product by x, y, alpha with the product by j equals greater than equal to 1 by 1 minus xi yj to the 1 by alpha. Okay, so it's a very different kind of deformation of the Schur case, as you can see. So if you set alpha equal to 1, this will become 1, and you will get the Hall inner product, and this will also become 1 by 1 minus xi. And this is the analogous theorem. So let u lambda and v lambda be q alpha bases of, let's say, lambda n to alpha, so indexed by let me just say,
Sorry, that's just the binomial series expansion, right?
which one?
Pi.
Here, yes, the generalized one, yeah, because
Right.
indexed by partitions. Then u lambda v mu is delta lambda mu if and only if sum over lambda u lambda of x v lambda of y is pi x y. Okay, so again, natural generalization. And to define the Jack symmetric functions, P lambda, here the convention is to, McDonald's convention is to put an alpha upstairs instead of inside the brackets, are characterized by two properties. This mimics what I said for the Hall Littlewood's, but I didn't write down explicitly. They have a basis expansion in the monomials where the first term is n lambda with coefficient 1, and all the other terms have a mu less than lambda. I mean, have u alpha lambda mu, and this is the first. And the second is that for lambda not equal to mu, p lambda alpha, p mu alpha, alpha. So they are orthogonal. So orthogonality and this kind of property.
And where do these scalars these are scalars, right? Belong Q alpha.
Which one?
The U lambda mu alpha.
They live in the fraction form. So in Q alpha.
Okay.
Yeah. So so it turns out that these also can be described combinatorially, and their their expansion is also a bit messy. So maybe I'll just show you on Sage first how to define that. So unfortunately, Sage uses the same parameter t instead of alpha to define. So you cannot muck around with this. I mean, I tried. If you use some other variable, Sage complains. So we have to use the same thing. So so the way you define them is using sim.jack.p because there are several jack polynomials. So this is how it looks like. And if you look at their expansion in terms of the monomials, they're quite messy. So even for in 3 variables, you know, you have all these horrible fractions, and you know, it gets worse. You know, Sage doesn't simplify things. And these J's are just integral versions of these. They look a little nicer because you've kind of multiplied out. Okay, so I started late, so maybe I'll give one motivation for the Jack polynomials. It's not really the original motivation at all, but so let me say something about the Selberg integral.
By the way, so then again, like what Amri had said that time, the characterization is unique, but then you have to prove existence.
Yes, exactly. Yeah. So that's again the interesting part. And as I mentioned, even for the Hall Littlewoods characterization like this holds, for the p lambdas where you replace alpha by t.
Will you do either of them, or
sorry?
Where will they be? Where are these found, or will you do either of them? Or?
Where are what? Sorry.
The proof of existence.
So so the thing is, if one does it for the McDonald polynomials,
right,
all of these are special cases. So one is done. So McDonald realized that, kind of understood that these are all seem to be manifestations of one single phenomenon, and that's kind of the viewpoint now.
Yeah. Okay.
Okay, so let me say a little bit about the Selberg integral. I will probably not have enough time to say everything about it, but so recall the beta integral, which is integral 0 to 1 t to the alpha minus 1 1 minus t to the beta minus 1 dt. This is gamma of alpha gamma of beta divided by gamma of alpha plus beta, where alpha beta live in the upper half plane. So real of alpha and real of beta is strictly positive. So the n-dimensional generalization of this is the famous Selberg integral. So the Selberg integral formula is the following. So integral 0 to 1 dt1, etc. Integral 0 to 1 dtn. So it's an n-dimensional integral. Product I equals 1 to n, ti to the alpha minus 1, 1 minus ti to the beta minus 1. So this product is over here. And then I have this A delta, which is the Vandermonde raised to the 2 gamma. So there are 3 parameters here. So Sn alpha beta gamma, this is equal to this. So where this product I less than j Ti minus Ti. Okay. And Selberg's integral formula states that this is equal to this product formula, j equals 0 to n minus 1, gamma of alpha plus j gamma. Sorry, so there are two gammas. This is the capital gamma function, and the small gamma is just a parameter. Gamma of beta plus j gamma, gamma of 1 plus j plus 1 divided by gamma of alpha plus beta plus n plus j minus 1 gamma. So if you set n equal to 1, j becomes 0 and you get this. Okay. These two will cancel. Okay. So this is so Selberg apparently first published this in 1944 in some Norwegian journal. He did not think this was terribly important, so he just this came up in some number theory work that he was doing, but he didn't think it was super important. But in the 70s, it became very important in statistical physics. You know, various models of interacting particles and random matrix theory and many other areas, including symmetric functions. So our motto generalize this to the following formula. So again, so I'll call with some abuse of notation, maybe I'll call this product also Sn. So our motto generalize this to the following formula: 0 to 1 dt1, etc. 0 to 1 dtn. Product. Now there's a new another parameter k, I equals 1 to k ti, and the product I equals 1 to n ti to the alpha minus 1, 1 minus ti to the beta minus 1, a delta to the 2. So this part is all the same. What is extra is this product of t1 up to tk. Of course, you realize that these are all symmetric. So, you know, you could have replaced t1 up to tk to whatever, tn minus k plus 1 to tn. You know, you could choose whatever k of them. And what our motto showed was that this is equal to the same product that we had before, Sn alpha beta gamma times the product j equals 1 to k. Now you have some extra factor, alpha plus j minus n minus j times gamma divided by alpha plus beta plus 2n minus j. Okay.
Sorry,
And
K here I get to choose? Is it?
yes, k is arbitrary. Yes. So yeah, so if you set k to 0, you get that. So you get this ability. Right. And so what McDonald realized is that this can be generalized to an integral involving Jack symmetric functions. And in particular, this product of TIs is nothing but one term in an elementary symmetric function, and the Jack polynomials degenerate to the elementary symmetric functions when you take the column partition. So maybe without going into details, I'll just say, can I take 2 more minutes, Venkatesh?
Yes, yes. No,
Okay. Yeah, sorry for going over time, but I think it's better to finish the story over here. So McDonald generalized this to p lambda alpha. So the first thing to notice, which I'll leave as an exercise, is that if you take p alpha of 1 to the n of x, you get the elementary symmetric function x. And this thing is just an elementary symmetric function, one term in an elementary symmetric function, and each term in the elementary symmetric function will give you the same answer. And somehow he kind of visualized all this in some way, and he came up with this conjecture. So this is known as Cadell's integral, but Cadell's contribution is quote unquote only to prove prove this formula. So this was conjectured by him. So this is the following. So what he realized is you have to tune the parameter gamma to the parameter of the Jack symmetric function. So again, let me write the same old thing: integral 0 to 1 dt1 up to 0 to 1 dtn. And what you do is you take p lambda of 1 by gamma, the parameter alpha you replace by 1 by gamma, in terms of the variables t1 up to tn, and the same other things. So product I equals 1 to n, ti to the alpha minus 1, 1 minus ti to beta minus 1, a delta to the 2 gamma, and this is equal to some extra factors. Again, linear in the parameters, times p lambda 1 by gamma evaluated at all parameters equal to 1, n of them, times Sn. These factors will take some time to describe, so I'd rather not do it now. Okay, so I'll show you. I programmed this in Sage. So I computed this. This program Selberg integral computes the Selberg integral in terms of n alpha beta gamma, and you get, so these are all 1 by some integers. So I took 1 by these guys, and here is the Selberg formula. Again, I took 1 by those guys, and you can see that they are the same. And I did it for different values of a, b, g. Then I defined the Aomoto integral. Now this involves this extra parameter k, and again I tried this for. So this computes the actual integral, and the Aomoto formula computes the product. And again, you can see that they are the same. I did not yet program the Jack polynomials. Maybe I'll do it in the afternoon before I send it over. Okay, so I think I'm way over time. I'm sorry about that. So let me stop. Thank you.
Any questions or comments?
Can I ask, is there an analog of that Folk's conjecture for Jack polynomials?
For what?
For Jacks.
For Jacks. I don't. Oh, yes. There's no conjecture. There's an explicit formula which I ran out of time
for Jacks,
yeah.
In terms of Shores.
Oh no, sorry. No, in terms of monomials. Yeah, I'm not really sure what is the status of it. So maybe let's check. So if I do Jack, it's sure in terms of Jacks. No, it's not so nice.
No, this is expanding Jacks in terms of Shores or Shores in terms of Jacks?
In terms of Jacks. I can go
and
there.
If oh, right. So that's Folk's conjecture, Shores in terms of Jacks.
I think it's not nice either.
But if you specialize T to 1, you get n factorial everywhere?
Huh? Why do you say that? Why would you expect n factorial everywhere?
Well, just because, you know, there's a conjecture for expansion of McDonald polynomials in terms of the big Schurs. And so I'm trying to relate it to that.
Okay, we can try that. So, so if I define a new, so if I call JP1, Jack's evaluated at 1, right? Then I'll do JP1 just to verify. So this takes t equals 1. And now if I do JP1 in terms of Schurs, I get diagonal. Right, so I would, no, and I don't see why you expect in fact.
No, that's,
No,
I don't know. I don't know. Yeah.
They'll become equal to Schurs, right? I mean, so I mean,
Yeah.
if you,
Yeah.
I mean, if you set alpha equal to 1, this will become. This will become,
Yeah. No, I would have to rewrite things a bit. I don't know how to ask a good question in terms of the sage here. Yeah.
oh, okay. No, but I'm just saying if you set alpha equal to 1.
No, I don't want to set alpha equal to 1. I want to. Yeah, I don't know how to say what I want to do.
Okay. So you want to express in terms of the big Schurs.
In terms of the big Schurs, yes, but yes, but then I don't know what is the relation between alpha in the Jacks and T in the big Schurs.
Yeah.
So I have to figure it out. So I don't know. Yeah.
Okay. Yes. Yeah, I didn't talk about the big Schurs.
Yeah.
So yeah, there is another identity. I mean, there is this kind of identity also involving big Schurs. Yeah. Would take some time to define. Yeah.
Any more questions?
I don't have a question. I just want to look at the Selberg integral formula.
Sure. Yeah. Yeah.
Okay, and then in the very last thing, so in the okay, so in Aomoto's generalization, so there's on the right hand side that product, and then there is another product, which is that thing here.
Yeah, that thing.
And so Sn occurs in the Cadell integral as well.
Yes.
And the other product that you added on, that is part of these explicit terms.
Yeah. That is what this will degenerate to. So this so here you will get.
So the extra factors times the p lambda 1 over gamma will degenerate to this product. That's what.
No. So if I just say take lambda 1 to the n, I'll get the same integral Hajar times.
There's a bunch of terms. Sorry.
Yeah, and that will just be added to this factor over here.
Okay.
And these other factors will become this factor. I mean, they're basically Pochhammer symbols, but notationally heavy. But it's all nice products. I mean, nothing.
They're Pochhammers.
Yes. Yeah, maybe I should say nice factors.
Okay, very good.
It's to say it's not something ugly. I mean, it's really. So this was somehow, yeah, as I said, it's called Cadell's integral. Cadell proved it, but.
I mean, I of course assume that those factors are explicitly described by either McDonald or by Cadell. So,
by the?
I mean, they're explicitly described. Yeah, they're not just there exist constants kind of.
No.
Yeah, exactly. That I figured, but yeah. So these are
some product of ratios of.
Right. And can I just copy down the definition of the beta integral?
Of what?
The beta integral, just a few lines ago.
Yeah.
Yeah, thank you.
Yeah, sorry. So this whole Jack polynomial business is not completely satisfactory because I didn't delve too much into it, but I thought it's better to go to McDonald's. So in the next week I will show you how to compute the monomial expansion of Jack polynomials, similar to what we did for Hall-Littlewoods. Again, very nice combinatorial interpretations involving the hook lengths, and then then it's just McDonald law.
Okay, any more questions? If not, let's thank Arvind.